Welcome back, game theorists. So now we know how to depict simultaneous move games. Let's talk about solving them. Our main tool here is what's called the Nash equilibrium. Now, importantly, the Nash equilibrium is the strategies, not the payoffs. Sometimes two different strategies lead to the same payoffs, but the strategies themselves are always unique. That's why the list strategy is always going to be unambiguous, and that's why it's strategies, not payoffs, that are the Nash equilibrium. So for notation, I'll often just write Nash equilibrium as NE. So it means that no single player can switch strategies and get a bigger payoff. Now, if changing a strategy gives you the same payoff, that's okay. Just means that you can't get a higher payoff by doing something differently. There is an equivalent definition that we'll talk about in some other part of the chapter. That is that every player's strategy is a best response to everyone else's strategy. It's often referred to as playing mutual best responses. So let's look at what is possibly the most famous example in game theory, the prisoner's dilemma. So we have two prisoners. Let's see, who are some of my students who would volunteer in last semester? I don't think I've used Ty in an example yet, so let's say Ty is one of the prisoners. And Ty can either confess or not confess. So, you probably saw a story earlier in Principles. I'll just remind you of it briefly. So the police have caught two criminals on a small minor charge. They suspect that they've worked together on something much bigger as well. However, they can only prove the smaller crime. They don't have evidence enough to convict them on the bigger crime. So what they do is they question each prisoner separately and try to extract a confession. Let's see, who is our second prisoner? Let's say our second prisoner is is Rachel. So Rachel can either confess or not confess. So if they both don't confess, they both get 1 year in prison for the smaller crime that the police know they have committed. So 1 year in prison will model that as being a payoff of -1. Now, if Ty confesses, then Ty gets to go free. Remember, we always have the role player's payoff come first. So always row player, then column player. So Ty is stretched here on the rows, so Ty is the row player. If Ty gets 0 years of prison, that gets a payoff of 0. They use Ty's testimony to convict Rachel for the bigger crime, and she goes to prison for 20 years. We'll call that -20. The game is symmetric, so if Rachel's the one who confesses, then she gets to go free, and Ty is the one who gets 20 years in prison. So remember, it's always row player, then column player, so this means Ty goes to jail for 20 years, and Rachel gets 0 years. The twist, though, in the prisoner's dilemma is that if both players confess, then they both get convicted of the major crime. Let's say both get 12 years in prison in that case. So as you might recall from principles, there's the cooperative outcome where they both would not confess and both get only 1 year in prison. However, that cooperative outcome is not a Nash equilibrium. So that's an abbreviation here, not a NE, not a Nash equilibrium. Why is that? Well, to be a Nash equilibrium, no single player can change strategies and get a bigger payoff. So just gotta look at that cell here in the table for not. And you can see that actually both players can change strategies and do better for themselves. So if Rachel is playing not confess, Ty could switch to playing confess and get a payoff of 0 instead of -1. Again, Ty's payoffs come first because Ty is the row player. And also, well, actually that'd be sufficient to show it's not a Nash equilibrium. You just gotta find one player who could deviate in one way, and that's enough to show it's not an equilibrium. Just to complete the example though, I'll also show you that you can look at Rachel's payoffs as well, and also show that she could also benefit by changing strategies. So if we're suggesting not could be an equilibrium, we then look, could Rachel change strategies and do better? And the answer is yes. So right now in not, Rachel's getting -1. Rachel is our column player, so her payoffs come second. If she plays confess, while Ty is still playing not, then she's getting 0 instead of -1. That's an improvement. All right, so not is, you might say, not is not an equilibrium. So how do we find Nash equilibria? I'll introduce three tools to you guys, and that'll help us find Nash equilibria in these kinds of games. Oh, but first, one more example. So I mentioned in my definition that to be a Nash equilibrium, it means that no individual can get a bigger payoff from changing strategies. It's okay if changing strategies gives you an equal payoff. Let me show you an example of that. So let's say our row player can play A, B, or C, and our column player can play X or Y. And let's say the payoffs are as follows. Let's see, who are my row and column players? Let's have Joanne be our row player, and Jerry is our column player. So it turns out that Bx is a Nash equilibrium in this game. So if Joanne plays B and Jerry plays X, Joanne's our row player, and row players' payoffs always come first. Joanne gets the 0, and Jerry gets 7. That's because no one can switch strategies and get a bigger payoff. So Jerry, if we're starting over here, Jerry could switch to playing Y. Jerry's our column player, and the column player's payoffs come second. If Jerry starts playing Y, he's going to get 1 instead of getting 7. He wouldn't want to do that. That lowers his payoff. If Joanne switched from, we're going back to Bx here, because Bx is our candidate equilibrium. I say candidate because we're still verifying as an equilibrium. So until we verify, let's call it candidate. So right now she's getting 0 in this candidate equilibrium. If she switches to playing C instead, she gets -1. That's worse. So last possibility, Joanne could also switch from B to A. That gives her the same payoff, but it's not a higher payoff. It's the same payoff, so that is not violating our definition of a Nash equilibrium. So Bx is a Nash equilibrium. We verified it now. Alright, so in our next episode, we'll talk about the tools for finding Nash equilibria. So here I just told you this is a Nash equilibrium, I verified it, but there's a way to find them more systematically.